Yeah, I'm going to do something that's always the interest, which is a live demo, right? So because, well, what's the point of only me having nice CPUs and GPUs? Why not make them available to everybody else? So if you want to run a lot of GPUs fairly easily, you can do that. And as of yesterday, there's a nice CloudFormation template. And you should be able to use that. Now, let me make sure first I get everything properly set up. So there will be a live demo at some point. But let's start with something that's maybe a little bit more, let's say, scholarly. So this talks really two pieces. So the first piece is a little bit how you can actually do interesting machine learning for personalization, deep learning for personalization. This is, in a way, one of the places where deep learning hasn't really had quite as much impact yet. There is some very nice work that recently came out of YouTube, nice work that came out of Microsoft in the context of deep advertising and YouTube movie recommendation, but I think there's a lot more that can be done. So I'll give you a quick overview, and then we'll go to a little bit more details about MXNet, how you can use it very easily, and, well, let's get started. So, as promised, two pieces. And so I'll start with personalization. So you've probably already seen before in the Netflix talks and so on, you want to have content relevant and interest relevant recommendations. And, well, Kindle, for whatever reason, recommends me those books. But what's really going on behind the scenes? And there's one thing that I believe a lot of people have ignored when they build recommender systems, and that's really time. So, in other words, when I have purchases, likes, app use, emails, ad clicks, queries, ratings, they're all time dependent. Now, you can always go and add a time feature, right? You can, for instance, add a time feature, and then you can learn that maybe on Sundays, I don't actually go and maybe, go to the office quite that often, right? Or, for instance, that, maybe on Mondays I will probably not, surf, Netflix or whatever while I'm in the office, right? You can learn those things. And that's kind of an obvious thing, but what it doesn't do is it doesn't get some context information very easily where if I do one thing, then another thing is likely to follow. Or if I buy a Micro Four Thirds camera, chances are that I'll buy the corresponding lenses thereafter, right? That type of sequence behavior is not so easy to capture with that. Or if I receive an email, I'm likely to respond to that person. Yes, I can have a received from that sender feature that I can hand engineer, but how many times can you do that before your engineers get sick and tired? So people have actually started using that by using basically very simple parametric models to model what's going on behind the scenes. So for instance, there's clustering, and then the time-dependent counterpart, which are basically, well, Markov models, right? So it's just Markov state transitions. For instance, if you have a traffic light, it goes between the three colors. And I can use similar things, for instance, to model search behavior. So for instance, I can model that I might have a navigational, informational, or other types of queries, and people have done lots of interesting studies with that. For instance, session modeling for web search is one of those examples. Likewise, you can be a little bit more nuanced and assume that the users who perform search, who visit web pages and other things, have a portfolio of interests. And their activity then depends very much on what types of interests they have as a function of time. And we did this, and you get very amusing behavior, like you can see that for a user, this is fully unsupervised, mind you. Some user goes and maybe first he's interested mostly in sports, then he realizes that he doesn't have so much money, and then you go off and he starts searching for jobs. And this was basically based on search queries that I did in the previous life. So this was prior to Amazon. Or if you have trajectory, for instance, for mobile devices, you can use Kalman filters and use them for location modeling. And then since people don't just go straight through walls, but usually tend to avoid them, you're probably going to get nonlinear models for trajectory modeling. So what really happens is that you have behind the scenes some explanatory variable that captures some part of the internal state of the user. And this is a time-dependent function. And then I have actions that are taken where I can observe those actions, or at least the effects of those. And the actions influence the future internal state. But also the internal state gets propagated forward and also influences what the next action is. So this lattice that you're seeing at the very bottom is basically just a dependency graph that makes sense in terms of causality. As in, you cannot undo the past by taking a future action, right? But the obvious question is, these are beautiful theoretical parametric models, and you can write wonderful papers and you can get PhDs for that. But are those models really true? And I'm guilty of that crime. I've written plenty of papers using exactly those models, but at some point you've got to ask yourself, well, do I really believe that I can model a user through a topic model, or a time-dependent topic model, a time-variant-dependent topic model, or anything more complicated? No. Well, maybe not. So what you can do is you can either say, well, hey, let's use just a simple non-parametric model where I have some latent state variable, have some observation, and the next latent state is given by some function of the observation and the previous latent state, and the same thing applies to, well, the observations. So H is hidden, X is observed. And I can do that, and I can basically directly regress on that, and to some extent, this sidesteps all the approximate inference problems. An alternative direction that I could go is I could say, well, hey, all those parametric models, like clustering or whatever, they are very nice, but they're actually embedded in a larger space. And then I use fairly advanced math to obtain what's called usually spectral methods. So Animan Kumar, I think, gave a talk here last year, and she's done great work on that. And basically, either embedding in a larger space or going directly non-parametric is one of the ways how to work around it. Okay, so now you're wondering, after all this essentially statistics background, what on earth does this have to do with neural networks? Okay, there we go. I could just model this non-parametric dependence through a recurrent neural network, or I could basically have a recurrent neural network with some attention mechanism, which tells me, how important the past observation is, or how much a particular action actually affects future observations. And then this way I can learn when to update state, how to read it out, and all of that. And, well, it turns out that this actually was a paper that was way more seminal than the authors at the time probably also thought. And essentially what they did is they said, well, let's actually model our latent state model just like a memory cell. So you have an input gate, a forget gate, and an output gate, right? And the equations on the lower right are kind of nice to have, but what you really want to do is you treat it as a black box. Because chances are that in most toolboxes, you have a good implementation of those things already there, so just treat it as a black box. At least start with that, then start hacking it. Right? Now, let me show you what this actually does in practice. This is quite powerful. So, if you were to look at user engagement, so basically, this is an example from Taotiao. So they have this news app, and you open it up, and then you shut it down, open it up, shut it down. And they want to find out, is the user going to come back? When's the user going to come back? Maybe never, maybe next week. And the problem is that user engagement is actually a gradual thing. So for instance, people have expressed all sorts of angst about how many users does Twitter actually have, right? And you've seen the numbers being all over the place. And part of the reason is because you could ask, how many accounts does Twitter have? How many users have opened the Twitter app this year, this month, this week, today? How many users have posted? How many users posted this year? And depending on how you set this up, you will get very different engagement numbers. And they're all true, and they're all kind of useless, except that, yeah, if they go down, it's bad. If they go up, it's good. Right? So what really happens is that abandonment in an app is a passive thing. Right? It's not that you actively decide, I've had it with Facebook, I will never open Facebook again in my life. It's just that, well, you don't open it, right? Or Pinterest or Skype or whatever. Now, all the engagement models that people usually use are active ones, where you have an active engagement. act of disengagement. So that's what you do when you call Comcast and try to get rid of their service, or AT&T, or your insurance, or anything of that form, right? You actually need to pick up the phone and say, well, goodbye, I've had it. But on an app, it's the other way around. So what we had to do is we basically had to turn those models on their head. So what we really had to do is basically treat this as a survival analysis problem of how long will the user survive until he uses the app again. Now, a couple of things that are important: world events like an election, user habits, am I a night owl, am I a morning person, or basically, did I see really awful content before, am I going to go back for that reason? So, this is probably the equation with the most scary math in the entire set of slides, but it's not scary. It's what's called survival analysis. So, atoms decay based on survival analysis, where you basically assume that the rate of decay for any atom is independent of how long it's been around so far. And then, so it's basically therefore this very nice exponential decay. Cancer patients, if you want to find out whether a drug works, well, you can only observe them for a certain amount of time. After that time, you can't go and just kill all the patients to make your math work out, right? You basically need to only look at the time, that you observed, maybe 2-3 years, and you look at when the patients died within that time. Users, when they open an app, this is another way you can model this. Funnily enough, it also works for modeling marriage to Japanese women, because for them, usually marriage is a terminal state, so the divorce rate in Japan is very low, and you can actually use hazard regression for that. So there's... Okay, fine. So here's what we do for session modeling. Basically, we essentially look at the time that it takes between when a user ends an app and when he starts it up again. And we then basically look at the hazard rate, basically the time that it takes between when the app is closed, when it is opened up again. So this is then a good way of modeling user activity. And what I can do is I have some external features, I have some internal user state, and have some time attributes in addition to that. I take all of those, feed them into a hidden state, and then use a recurrent latent variable model, so just like what I described before, to model this. Okay, this sounds kind of complicated. Here's what it is if you have many users, because all those users draw upon a common world state that is commonly learned, but their internal state depends on the user itself. Okay, so you then just take that big beast, you throw backprop at it, an SGD, and you wait, and you get nice results. And so those results, those numbers on the bottom, basically the lower right, small numbers are good. It's basically the amount of surprise. It's how little you can explain how well when a user comes back. And what you can see is that if you have an LSTM, that actually fits things quite well. Now, from the top to the bottom, this is actually what we did. We spent about 3 months doing heavy-duty feature engineering, doing all the nice things that you would do as a good statistician. So in a way, this is one of the most depressing tables I've ever seen, right? Because we spent all this time, and then we took us about 3 weeks to run an LSTM, and it just blew everything else out of the water. So the morale of the story here is, don't do feature engineering. Or at least before you do explicit feature engineering, just throw a nonparametric model at it and wait what it does, right? And hey, it worked. And okay, there's some more curves and they all show that it works nicely, but this is a very simple idea. Now, this is a fun diagram. So the purple curves that you see, these are the hazard rates that we estimate. The blue vertical lines is when the user actually comes back, and the red line is basically e to the minus the integral of this purple line. So this is basically the survival function. And what you can see is that we sort of kind of get the times when a user is likely to come back. At least, the peaks coincide nicely when a user comes back. That doesn't mean that this is the only time when a user does come back, but it kind of captures it rather nicely. And you can see that, you have all the nice periodicities and all those features in there. So in other words, you can see that, the system learns that there are 24 hours in a day and 7 days in a week. And depending on the user, you'll see that maybe the first one might actually be somebody who opens the app right in the morning and then in the evening when he comes home, whereas the next one on the right only opens it in the evening, right? So you get all those effects rather nicely, and you don't have to do any feature engineering. Okay, which is kind of cool. Now let's look at something else, recommender systems. And first of all, just before I get into this, many, many thanks to Netflix for making the Netflix dataset available. However, the Netflix contest, the way how it was posed, is essentially recommendation archaeology, not recommender systems. Okay. In other words, what it did is it gave the data for a large range of time, and then it said, well, for a subset of those user-movie interactions, predict the ratings. Right? Now, the problem is, if I know that the movie is going to be a blockbuster, I know that you're probably going to like it, right? Or if I know what the election outcome is, then, well, I probably would know that I should have sold stocks before, right? At least, stocks that matter here. So let me put this into pictures. What really happens is, so the red line is the testing data, the blue line is the training data, and mind you, it's a log plot. But what you basically see is that, we have a non-trivial amount of data from 2006. And of course, we can use that to find out what the user might have liked in 2003, right? So that's kind of a little bit questionable. So what you should be doing instead is you should actually make a hard cut, let's say at 2004, use all the data up to 2004 in order to predict 2005 and so on. So basically, you don't have in practice the luxury of looking forward. Okay, so here's how you get it right. And this is unfortunately still a little bit of a monster of a model. So this is coming out at Wisdom 2017, just like the previous papers. If you want to know all the details, come to the conference. But basically, here's what we did. We assumed that user states can change over time. Well, that's exactly like what I mentioned before, except that now we said, well, hey, we have no idea exactly what the user state is, so let's just make it non-parametric. Okay. Furthermore, we assume that item states change over time. So you would basically therefore assume that even though, let's say, that movie, that book, or whatever is the same throughout, additional side information or maybe additional events may make a movie more relevant or not. And then what happens at the time of recommendation? You take the user attribute, you take the movie attribute, you combine them and compose it into a rating, and that's it. But the downside of this is, of course, that now you get lots of interdependent effects between user states and movie states, as they are a function of time. And right now, training that is still a little bit of a beast, and well, stay tuned for tricks on how to do it better. Because right now, as you can easily see, the backprop makes it very costly. That's it. What you get is models that actually are very compact, but also fairly accurate. Now, if you've ever participated in the Netflix contest, you would think that, well, actually those numbers are quite lousy, right? Because, hey, somewhere between 0.94 and 0.945 is not a terribly good recommendation accuracy. Well, yes, because that's exactly the difference between predicting the future and explaining the past. With the benefit of hindsight, I can do much better. That's like all the analysts now saying why Trump won. With the benefit of hindsight, yeah, that makes the analysis so much easier, right? Well, that's it. We compare to all the other models that presumably take time into account, like PMF, time, SVD, and all those models have much bigger parameter spaces, and they work worse. So that's reasonably good validation that we're onto something useful here. Now, here's a fun one. Who remembers the Oscars from last year? Well, probably very few hands go up. And this is consistent with what you're seeing there. What we did is we basically picked movies that had a non-trivial amount of time variance, which just so happened to be the movies that actually got awards. And what happens there is we basically plotted the average score that users would give a particular movie as a function of time. So we asked for a given user, how would you rate that movie? And we plotted that as a time varying function and we averaged over the users. So this is the same movie, the same user, just at different points in time. And so what happens is, first of all, the green line in the bottom means, well, hey, ratings of movies pretty much don't change. However, for those specific movies, you can see a significant uptick around the time when they got the award, and then afterwards it flattens out again. More to the point, after 12 months, the line's back to where it started, which is consistent with the fact that essentially nobody remembers what last year's Oscars were, right? But the thing is, like, well, even if you don't like Titanic or Life is Beautiful or whatever, you would never dare telling people that Titanic was an awful movie, right? Because everybody will go like, this guy doesn't understand movies, right? And this is exactly the confirmation bias. So if somebody tells you this is good, you're also going to agree, right? And that's exactly what we're seeing here. Now, the cool thing about this is we didn't have to hand engineer this in, right? So we didn't have to figure out that there are confirmation biases, there is maybe hedonic adjustment and other things that usually people have to think about and invent. We just use the data, so this makes us very lazy, but the computers have to work a bit harder. Sanity check, we basically looked at how much better do we do for different movies, and yeah, okay, basically you can look at the various scores and you can see that RRN, recurrent recommender networks, works better than others, but basically what you can see is that it works better, especially for movies where the rating fluctuates a lot. So for those, we catch it early, which is kind of what you want, right? So this gets me to the second part of the talk, deep learning with MXNet. And so this is going to raise the obvious question, given that we saw Ratchet just doing a Q&A and, well, a beautiful talk in the morning. Why do we need yet another deep learning tool, right? Okay, so a couple of reasons, and I hope I'll convince you of it. So one thing is, MXNet's actually amazingly resource efficient. So it's engineered for cheap GPUs with small memory footprint on slow networks. In other words, the stuff that you might have at home rather than stuff that you might only get on a company internal supercomputing center, right? So try this at home under your desk, that's fine. The second thing is even on lots of GPUs, it's very fast, and I'll show you some nice numbers in a moment. But basically, we get linear scaling with number of machines and number of GPUs. And moreover, actually writing code in it is very simple, because you can mix decorative and imperative code, and I'll get a little bit into the differences between the two. The reason why it works with all those languages, C++, Python, Scala, R, Julia, MATLAB, JavaScript, Go, and a few others, is because they all invoke the same backend, which then takes the computational graph, executes things, and if you have very specific language-specific constructs like in R, Julia, Python, or whatever, you can mix them in with that. Actually, that's where the name comes from, MXNet, MixNet, right? You can mix stuff. And this also means that if you want to deploy rather than on a GPU instance, on a CPU instance, or let's say on a mobile drone, well, all you need to change is the backend. Okay. So let me quickly walk you at least through one minor detail. That's imperative versus decorative. So imperative is how you would typically go and write, sensible Python code, for instance. You define one vector, you define another vector. You then define a third vector, which is the product of the two. You print something, and then you do something else with that vector, right? And this is very nice. It's very nice to program, fairly straightforward. You can take advantage of all the benefits that your language has. And unfortunately, it's a bear to optimize. But if you need the flexibility, there you go. Decorative is exactly the other end. You define some variables. You define how those things are combined. Then you say, well, now compile something out of those pieces. And then you define some other function that works on those pieces. And this is very nice in terms of optimization, but it's a little bit less flexible. So for instance, if you think about it, if you write cafe code, you're basically writing a decorative program about how your deep network structure is supposed to be. You basically write a little description which defines all the various layers, and if you use ResNet, that can turn into maybe 1,000 layers of code, depending on how efficient you are. Here, you just use your native language for it, and you can do that. Now, the key point is, sure, first of all, you can optimize this, but also you want to have really both. Because for the stuff that is very compute intensive, like layers, where you have a non-trivial computational graph, you want to have a nice decorative syntax. And mind you, yes, this may look really complicated, but you don't necessarily need one line of code for every module. If you have repeated modules, you just define one super module and we repeat this. This way you can actually do, for instance, Inception v3 on essentially one screen of code. And then on the other hand, to deal with things like, well, we actually need to iterate through the data, occasionally we need to reset it, we need to load it from different sources, well, that's exactly where you want to have all the flexibility that imperative programming can give you. Right? And so by having code that combines both, you actually get fairly nice and efficient system that doesn't get into your way. Okay, so here's an example, and I'm not going to bore you with all the details of it, but basically you can see that you can set up your data input, then you define your executor for how to go through the data, and then again you have an imperative part, which right now just so happens to be on the GPU, even though it's not terribly painful to do. So you just say, hey, on the GPU, update the parameters with learning rate times the gradients. So this is kind of very neat. Now, why would this help you? Well, for instance, if you have an LSTM and you apply it to sentences, then we all know that sentences have very different lengths. Some are short, some are extremely long and keep on going on and on and on forever, and you would really want to make sure that all the short sentences are in one place and all the long sentences are in another place for the purpose of mini batches. 10 lines of extra code, let you do all that bucketing, and then you're back to your imperative part. That's your decorative part. Or if you want to do fun things like 3D reconstruction, well, it's like 100 lines of code. You should check out the GitHub repository for that, and then you can turn your standard 2D images into 3D. Okay. Now, how do you do it in practice? Well, what you have is, if you recall from some of the past talks, you have this notion of a parameter server. And I still believe that a parameter server is actually fairly useful as a metaphor for synchronizing things, because it lets you reason about code and data flow in a fairly efficient way. And I believe this is also partially at the heart of why we get this rather nice performance that I'll show you in a moment. But basically you have workers synchronizing against parameter holders. Now, those parameter servers on top, they don't need to be separate machines. They can be physically located in some of the workers, but logically they're separate units. And then if you have multiple GPUs, you would go and synchronize the GPUs either with peer-to-peer or through memory. And that decision is really an engineering decision based on what type of hardware you have. Okay. Now, how do you do multi-GPU code? Well, you change 2 lines of code. Set number of GPUs, in this case 4, go through the entire device context, and then you let it run. So it's fairly painless. Okay. Now, this is, of course, the number that I guess everybody's wondering about. So what we did is we took 128 GPUs, and this is the aggregate throughput on ImageNet, and we compared AlexNet, Inception v3, and ResNet 50. And so the speed up that we get is the curve on the right. So this is basically log plot. So that's why it goes from 10 to the 0 to 10 to the 2, because we took up to 128 GPUs. So this is on our latest P2 16x large instances that came out about 2-3 weeks ago. And what you see is that for AlexNet, on 128 GPUs, you get a 70-fold speed up. And for Inception and ResNet, you get essentially 108-fold speed up. ResNet's a little bit slower because it's a more expensive architecture. Now, the interesting question, of course, is, why on earth do we have this huge dip between the first and the second GPU for AlexNet? Right. And then it's pretty much the same as for everything else. What happens here is something very simple. For one GPU, you can leave all the parameters on that same GPU. For two GPUs, you actually need to exchange between it. And that's effectively what slows it down. Now, why does this not happen for Inception and ResNet? Well, if you recall the network definitions for those networks, AlexNet has a fairly massive, fully connected layer in the end, right? And that large number of parameters and correspondingly very dense gradients and large gradients cause all that slowdown. So what you're seeing is that basically if you have a fairly parameter-heavy network, you will suffer a little bit more in terms of speed up, just because now you actually need to communicate more across the network. So that's essentially what you get there. Now, of course, the one thing that everybody would have been wondering about is the demo, and so I hope the gods of all the demos work. So there's something called a CloudFormation Template, and actually maybe I should go back and just point you to that first. So if you do a git clone from MXNet, or basically look for bit.ly deep CFN or bit.ly deep AMI. So deep AMI is basically an AMI that we built with all the deep learning toolkits in it, already pre-configured, pre-compiled, NVIDIA drivers in it, Python 2, Python 3, Anaconda, basically whatever you want as a data scientist. If you want something extra, well, post the feedback, we read it, we'll add, don't worry. The CloudFormation template then builds on top of that, and it lets you launch a lot of those things in one go. So I'll show you how to do that launching, but since it takes a few minutes, I'll just show you how to launch it, and then we'll have a go at it. Okay, so let's say create a stack, and this is, let me see whether I can change the resolution a little bit, because otherwise this is kind of awkward. Okay, I think this is better. Okay, so what I can do is I can basically use this CloudFormation template. So CloudFormation templates are basically a little piece of, well, JSON or basically simple YAML, which describe how various machines need to be launched together. So I've just taken the one that's already in the MXNet repository. Okay. And let's call this stack MLconf. Okay, since I don't want to burn up too many resources, let's pick maybe a couple of G2ATEX larges, and then I will go use my SSH key. Okay, let's make it open to the world. Usually that's not what you want to do. You want to actually put something there that matters. Let's say we pick 5 workers. This actually fires up 6 machines because it's number of workers plus 1. Then, well, you can set some additional keys and IAM roles and God knows whatever, which we don't all care. Yes, this will actually cost you money because we are launching real machines. And then it says create in progress, and it'll do something. And, over time, some machines will come up. Now, this takes, unfortunately, a while because it has to set up a VPN and all the bits and pieces that, basically you otherwise would have to configure manually. We've just made it easy for you to go out and say, hey, I need 16 machines with 16 GPUs each, and I need them for the next hour. Okay, here you go. Now, after you've done this, you will basically see something like this in your instance viewers. Yes, and we have a lot of them. And so what I'm going to do is I'm going to grab the machines that are called 16x large, 4 of them, sorry. Okay, there they are. And so there's a cluster that I allocated before, and that's basically 128 GPUs. Those 4 machines here. Sorry, 64 GPUs. Now, this is my gateway machine. This is the one that I can log into. And here's the IP number. And so what we can do now is we can simply log into this machine. SSH, EC2 user at. So now if the gods of the demo allow, yes, I'm in. Okay, so far so good. Now you could run TensorFlow and Torch and whatever else, but what we're actually going to do is we're going to run, well, in this case, MXNet. So a couple of variables set. So there are 4 workers and 16 machines. Okay, that's what I want. We're going to increase the verbosity level a little bit because, yeah, it's always a good idea to let the parameter server actually report something, because after all, it's a demo. And now what I could do is I could simply launch a script which will happily run something on CFAR. So now, I need to go to the right path, source. So here you can see a lot of other things. So Caffe, CNTK, Keras, TensorFlow, Torch, Theano, everything's there. And then let's go for it. And so now what you see is the various nodes have started up, and this is now unfortunately a bit boring because now it'll just run and do things. So I might as well use this time to take questions now while we watch Ashel right now starting up. The first time you run this, you'll see a lot of output because it's actually downloading the data first. And right now it's a little bit ugly because it downloads the data on every single worker entirely. If you were to do this on a large data set, you'd need to change the loading routine a little bit to have a subset of the data on each separate machine. And now there we go. We see that it happily processes things at, about 2,500 samples per second. That's per GPU. And we have 64 of them running right now. This is running live, and in a few minutes, you'll see that it's done. So this is training CFAR in a demo. Okay, so I just see the yellow light coming on. So let me quickly switch back to the talk. So obviously, the key points here is, MXNet.io. You'll find the code. Deep Army and Deep CFN will give you pointers to how to do this. Actually, the CFN is already in the MXNet repository, but you can use it for other things too, like TensorFlow. And, well, obviously, I didn't do all of that work by myself. The people who really deserve the credits are Hao Jing, Xiaoyan Wu, Alex Beutel, Amar Ahmed, Mu Li, Tianchi Chen, Bing Xu, Alexei, Joe Spicer, Naveen Swami, Anirudh Subramanian, and many, many more. And if you're looking for a job, you know how to code for deep learning, you know your way on GPUs, well, talk to us. Okay, that's all I had to say. Questions? I guess the key question will be, is it done? Well, got a few more iterations to go, but yes.
So have you guys done any benchmarks with MXNet versus the other papers?
Okay. I didn't pay you for asking this question, but thanks for asking. So you might wonder, first of all, why on earth are we not showing comparisons to TensorFlow? Okay, so actually, Ratchet's talk this morning made me feel a little bit better because we were actually getting not so insanely good speedups on the TensorFlow side. So the speedup was something between 50% and less than 50%, depending on the network, and we weren't quite sure whether we were doing something wrong. So I want to make sure that when we release those numbers, we're reasonably confident that we didn't screw up, and I didn't want to be unfair. That said, on a single machine, GPU by GPU, we are slightly faster. For multi-GPU, well, you saw the straight lines, as in linear scaling in our case, and They're not quite that straight in the other case. Basically, if you want to save considerable money on large-scale computation, there are a couple of scripts that might help you, right? Go and use them.
Thanks.
Yes?
For the first part of your talk, every time we do personalization, the level of sparsity will increase a lot, including the amount of missing values. For using LSTM, what was your motivation about this type of?
Okay, so the question is basically, what do we do about data sparsity? Well, data sparsity is a non-trivial issue. Because if you have a movie that was only shown twice or 3 times, then, well, you really don't know what it is. Unless it's called The Chainsaw Massacre Reloaded. Nobody's seen that movie because it doesn't exist, but everybody here smiled and started laughing when I mentioned the name, right? Because we all know what that movie is probably going to be about. Why do we know? Because we know from the title. If we then know who the actors are, we get a better idea. So if Brad Pitt occurs in it, it's a different story from if some no-named actor who you've never heard of is the lead, right? Now, what that basically means is you can use additional context to fill in. And for this, a lot of essentially transfer learning models may help you quite a bit. Or you basically take inspiration, for instance, in the work that's recently been done in character-based LSTM models for natural language, right? So they even throw the words away. So there's some very nice work that came out of Kyung-Yun Cho's group in New York, and also Wang Ling from DeepMind. So those are probably the 2 places where I would start, and I would use that to deal with sparsity. In addition to that, well, for the tail, sometimes you just can't do such a great job. In that case, all you do is you just say, well, for the tail, I'm just going to use a single parameter. So if you want to see how that is done with a bit more math, have a look at our de facto paper from Wisdom this year, and it'll walk you through all the details there. But that's, you need to see the equations, unfortunately. Yeah. Any other questions?